Hi everyone, it is our great pleasure to welcome Professor Todd Hyster. So he did his undergrad studies at University of Minnesota. In 2008, he did his grad study in Colorado State University, and the research is focusing on developing the rhodium catalyst CH activation reactions. After graduation, he joined the group of Francis Arnold at Caltech as an NIH postdoc fellow and involved P450S to catalyze the nitrogen transfer reactions. In 2015, he started his independent career at Princeton University, and in 2021, he moved to Cornell University, and currently he's an associate professor of chemistry and chemical biology. So Todd's group has developed photochemical strategies to expand the synthetic utility of common enzymes and enabling them to address long-standing selectivity challenges in the chemical synthesis in the previous researches. So today, Professor Hyster is giving us a talk about the photoenzymatic catalysts using the light to reveal new enzyme functions. So let's welcome him again and enjoy the talk.
Great. Cool. Hopefully everyone can see that. Yeah, thanks for the introduction and I guess for the opportunity to share with you all some of the work that we've been doing in my group in the area of photoenzymatic catalysis. And so I think when we think about organic chemistry, oftentimes we're thinking about developing new synthetic reactions, often developing new catalytic reactions. And I think when we think about catalysts, oftentimes we're thinking about things like transition metals, organocatalysts, or enzymes. And I think each of these have made important contributions in sort of the synthesis of a variety of compounds. But I think a question you might ask yourself is, if you want to develop a new catalytic reaction, how do you approach it using these catalyst platforms? And what I would say is that the approach is sort of different depending on the catalyst you're thinking about using, right? So for instance, if you're interested in, say, a transition metal catalyst, so what I'm depicting here is just a simple ligated rhodium complex. We know that rhodium has access to a few different fundamental mechanisms, right? Things like oxidative addition, migratory insertion, transmetallation, among a few others. And we know that these metals are able to facilitate these reaction mechanisms with a few different types, or with many different types of substrates. And so if you were to sort of merge all the possible substrates with all the possible mechanisms, right, you gain access to hundreds of new chemical reactions that you can think about designing. I think highlighting why transition metals are so powerful. In the realm of organocatalysis, you can take the same type of approach, right, where you can take something like a secondary amine, and when it reacts with a carbonyl, we know we can find an enamine, aminium, or you can oxidize the enamine to form a SOMO type intermediate. And again, these species can interact with a variety of different substrates, again, giving you access to hundreds of new chemical reactions. Now, in biocatalysis, we typically don't think of these enzymes as having access to many different types of mechanisms, right? We tend to think of enzymes as being very mechanism specific. And so just to sort of demonstrate this, if we think about a really common enzyme like a ketoreductase, the name sort of gives away the game, right? A ketoreductase reduces ketones and it uses the same mechanism every time, right? It's a hydride transfer to a carbonyl followed by a proton transfer. And so while this enzyme has been incredibly useful to synthetic organic chemists and can reduce a number of different types of ketones, it's really restricted to one reaction mechanism. And so the question that we've been asking in our group is it possible to sort of take a page out of transition metal catalysis and organocatalysis and think about enzymes having access to multiple mechanistic pathways? And then if we think about merging those possible mechanisms with other types of substrates, can that potentially give us access to completely new biocatalytic reactions that nature doesn't normally use for these types of reactions? And so, of course, we're not the only ones to think about this. I think you can break down the approaches based on the types of reactive intermediates that people are interested in using. So for instance, if you're interested in organometallic intermediates, individuals have developed natural and artificial metalloenzymes to catalyze a wide variety of different transformations. And in these cases, right, the metal cofactor is responsible for the reactivity, and the protein is really controlling elements of the reactivity of the metal complex, and then ultimately the selectivity of the transformation. If you're interested in closed-shelled intermediates, hydrolases, detomerases, and alblases have been developed for what I would consider to be classic organocatalytic transformations. And so when my group started, we became interested in whether we could think about other types of intermediates as being valuable in sort of expanding the functions available to enzymes. And in particular, we were drawn to the reactivity of organic free radicals. So these are, I think, fundamental species in organic synthesis. We tend to think of them as being reasonably high in energy. And I think with regards to reactivity, this is actually a really beneficial feature, because what it means is that the activation barrier for a wide variety of bond forming events tends to be quite low. And this is, of course, why radicals are so versatile in organic synthesis. The challenge lies if you're trying to control the selectivity of a radical reaction, because ultimately what you want to use is a catalyst to give you energy differences in diastereomeric transition states such that you can get high levels of enantioselectivity. And so it turns out that small molecule catalysts like Lewis acids and organocatalysts can sometimes provide high levels of enantioselectivity, but in general, small molecule catalysts really struggle to control radical intermediates. And so the question we had was, can we think about forming radicals within protein active sites? If we can, that would give proteins access to new types of chemical reactions, but it would also give us the opportunity to use directed evolution to solve selectivity challenges in organic synthesis and hopefully make impacts on that side of the project. And so we've done a lot of work with nicotinamide dependent enzymes. But ultimately, the enzyme family that has proven to be most general for us are these flavin-dependent ene reductases. So these are proteins that stereoselectively reduce activated alkenes with high levels of selectivity. You can buy large collections of them from your favorite enzyme vendor. And so to us, that ends up being a really attractive feature because it enables us to think about developing reactions that folks that don't have experience expressing proteins might be able to reproduce using a commercial kit. Now, these enzymes are incredibly substrate promiscuous, so they'll accommodate a wide variety of different functional groups as the electron withdrawing group, which makes them versatile for synthetic organic chemistry. They also reduce alkenes in a variety of different chemical environments. And so our thought is that this substrate promiscuity will both give us a broad substrate scope, but also help promote catalytic promiscuity. Now, the native mechanism does not involve radicals. It's a simple hydride transfer from flavin hydroquinone to this electrophilic beta position. This will form an enzyme-bound enolate, which will be protonated by tyrosine to give you the reduced product, at which point NADPH combined hydride will transfer from the C4 position to the flavin cofactor, turning flavin back into the flavin hydroquinone and priming the enzyme for another catalyst turnover. And so in the native mechanism, flavin moves back and forth between the hydroquinone and quinone oxidation states. But we know that flavin has access to a third oxidation state. It's the open shell semiquinone. And so in solution, we tend to think of the semiquinone as being fleetingly stable, engaging in comproportionation and disproportionation events to form the more stable flavin oxidation states. But it's known that enzymes are able to stabilize the semiquinone. And they do that because nature needs some way of moving electrons from 2 electron reductants like NADPH to 1 electron oxidants like metal centers. And they often use this flavin as a mediator for those electron transfer events. And so the question we had was, if it were to be possible to stabilize the semiquinone within an ene reductase, we could use the hydroquinone as a single electron reductant, and then the semiquinone as a hydrogen atom source to do reductive radical transformations asymmetrically within the active site. And so ultimately, we found that we could do this type of reactivity in this hydrodehalogenation. We confirmed mechanistically that this proceeds via radical intermediates, and the reaction occurs in high yields and excellent levels of enantioselectivity across a wide variety of different types of substrates. And so having demonstrated that we could actually do radical reactions within these active sites, we wanted to move to some reactivity that we found to be a little bit more interesting. And in particular, we were drawn to this reductive cyclization of this alpha chloroamide to provide a lactam that might have some value for pharmaceutically important molecules. And so we did an initial screen of 12 different wild type ene reductases that we prepared in-house, and unfortunately found that none of them gave any reactivity. And when we encounter this challenge, we tend to look to mechanism as the problem rather than substrate binding, mostly due to the fact that EREDs are so substrate promiscuous that we think they should be able to bind a wide variety of substrates. And it became pretty clear to us what the issue was. If you look at the oxidation potential of the flavin hydroquinone by comparison to the reduction potential of the alpha chloramide, what you'll quickly recognize is that electron transfer is uphill by over 25 kcals per mole, meaning practically this electron transfer won't occur without additional energy. And so the hypothesis was that, given that the hydroquinone absorbs right around 360 nanometers, if we were to irradiate these enzymes with light, potentially we could access the excited singlet or triplet state, and then this could ultimately drive the desired electron transfer event. And it turns out that this actually works quite nicely. We started off by using a 390 nanometer LED, and what we see is a step change in function. We're now getting product in 60% yield as a 2-to-1 ratio of the cyclized to reduced product, promising levels of enantioselectivity. And in the course of the optimization, what we ultimately found is that 497 nanometer cyan LEDs are actually better suited for this reaction, providing product in 89% yield, greater than 20-to-1 ratio of the cyclized to reduced product, and comparable levels of enantioselectivity. And so I thought it maybe would be best in light of time to not focus on the substrate scope, although it is quite broad, and instead focus on sort of the mechanism. And so if you look at the absorption spectra of the Flavin hydroquinone, what you'll notice is that there's negligible absorption around 500 nanometers, which was the best wavelength for this reaction. And so what this indicated to us is that the reaction mechanism is likely not as simple as we initially hypothesized. It likely doesn't involve direct excitation of the Flavin hydroquinone. And so we began looking for other species that would absorb in this region. And what we found is that when you tank the enzyme with the reduced Flavin hydroquinone cofactor and you add the alpha chloramide substrate, you see this new absorption feature. Now, we initially attributed this to a charge transfer complex, but the challenge with Flavin is that this absorption feature also looks very, very similar to the Flavin semiquinone. And so we wanted to rule out that this was just, a single electron oxidation of Flavin that was occurring maybe by some impurity. And so what we chose to do was add sodium benzoate to the reaction. And the thought is that sodium benzoate, as a function of being anionic, should be able to bind within the protein active site. And if this is a charge transfer complex, that absorption band should decrease as the alpha chloramide is kicked out of the active site. And that's exactly what we see. So you can see that absorption feature at about 497 nanometers decreased. And so we think collectively, this is good evidence for a charge transfer complex. And so when we encounter these in synthetic organic chemistry, often there is electron donor acceptor complexes where an electron donor and an electron acceptor aggregate in solution and their molecular orbitals actually mix. And so when you photoexcite these complexes, you're promoting an electron from the donor to the acceptor to give you a radical ion pair, and that ultimately goes on to do your reaction of interest. And so in our case, Flavin hydroquinone is actually functioning as the electron donor. Our substrate is the electron acceptor. And so when we photoexcite them, we're moving an electron onto our alpha chloramide and forming the Flavin semiquinone, which might explain why the CT complex closely resembles a Flavin semiquinone. But there's sort of an additional feature here that I think is really interesting. So if you were to tank FMN or riboflavin, reduce it to the hydroquinone oxidation state and add your substrate, you don't see a charge transfer complex. There's no interaction between the two in solution. And so it speaks to this idea that the enzyme is actually responsible for templating the charge transfer complex. So the enzyme is going to bind the cofactor with nanomolar affinity, bind our substrate with micromolar affinity. And when they're both within the active site, their molecular orbitals are forced to interact with one another and form the CT complex. And this ends up being a really, really attractive way of ensuring that radical formation only occurs within the protein active site. We've done some DFT calculations on models that we've prepared in-house. We would expect the absorption to be right around 510 nanometers. And so that sort of recapitulates what we see in our UV-Vis experiments. And so I don't have time to go through all of the cyclization reactions we've done. It works on a wide variety of different substrates. But I would say synthetically, it would be more valuable to us to be able to do an intermolecular reaction. So in this case, say a coupling of an alpha chloramide to an alkene. Now, the challenge here is that if we're going through radical intermediates that we know have short lifetimes, we need both substrates bound within the active site prior to radical formation. And given that we're working with an enzyme that only has a single substrate binding site, it wasn't clear to us that that would occur. And if that were the case, then you would expect to see this hydrodehalogenated product as the main byproduct of the reaction. Moreover, given that this is a fairly flexible substrate, it wasn't clear to us that we'd be able to set this gamma stereocenter. Regardless, we set out, tried the reaction with an alpha chloramide, 2.5 equivalents of alpha methylstyrene. We found that the same enzyme as before, with slightly modified reaction conditions, is able to catalyze the coupling in 97% yield, 98.2 ER. In our initial screen, we also identified another E-red homo analog called no stock ER. And when we introduce just one mutation into the active site, converting a tyrosine that could be a hydrogen atom source to a phenylalanine, we're able to access the opposite enantiomer in near quantitative yield and excellent levels of enantioselectivity. And so what I think was most striking to us is the yields in these reactions. We're seeing less than 5% of the hydrodehalogenated product in all cases. And so what this implies is that there's a control mechanism in this reaction. And so we went back to our UV-Vis experiments, and what we found, again, this is the absorption spectra of the Flavin hydroquinone. As expected, when we add the alpha-chloroamide to the reduced enzyme, we see a sort of a weakly absorbing CT complex right around 495 nanometers. And then when we add styrene, we see really a significant change in the absorption feature of that CT complex. We have something that absorbs now to a far greater degree than what you see in the absence of the alkene. And so we think that this is evidence for a higher order charge transfer complex, one that involves 3 components plus the enzyme. So we refer to it either as an enzyme templated ternary charge transfer complex or a quaternary complex. And so what we think is going on here is the enzyme in the presence of the alpha-chloroamide and the Flavin hydroquinone is able to form a charge transfer complex, but it has weak absorption properties. And it's really only when you have the alkene present that you have a species that absorbs light to such a high degree that it can actually be responsible for radical formation. And so of course, this ends up being really attractive because it means that both substrates have to be bound within the protein active site for radical formation to occur. And so this was unexpected, but a really great way of gating the electron transfer events. I don't have time to go through all of the substrate scope. It works for a variety of different amides. We can use non-styrenyl alkenes, unprotected allylic alcohols, allylic amines, molecules that have electron deficient and heterocycles all work quite nicely. And so this has proven to be a pretty general reaction, and we're trying to apply it to other types of synthetically valuable reactions as we speak. And so given sort of the goals of this center, I thought it would be useful to talk about another sort of approach to radical biocatalysis that we've been exploring in my group, which is this idea of trying to merge photoredox catalysis with biocatalysis to form radicals within protein active sites. And so the thought in this case is to take enzymes that have some sort of substrate binding site, and presumably the enzyme on its own couldn't do electron transfer events. And so if we were to add a photocatalyst to these reactions, we'd now have something that could function either as a reductant or an oxidant, and be able to in theory, help facilitate radical formation within the protein active site. Now, of course, the challenge in this case is if you've got an exogenous photocatalyst, it has the opportunity to do, say, a reduction in solution instead of doing reduction within the protein active site. And so how do we think about controlling these electron transfer events? Well, what we were hoping to take advantage of was the activation that's provided by the enzyme upon binding. So I think we can imagine a scenario where you might have a reductant in solution, where just the thermochemistry of doing an electron transfer to, say, a substrate, such as this alpha-acetoxy ketone, might be challenging. But upon binding, right, you gain hydrogen bonding interactions, there's changes in the electrostatic environment around the ketone, and that should activate the carbonyl for reduction. And so you can imagine in a scenario like this, reduction of the substrate in solution wouldn't occur and would actually only occur when the substrate is bound within the enzyme active site. And so we've referred to this as sort of enzymatic redox activation. And I think this general concept for us was really inspired by a couple of studies. The first of which is this really beautiful example by Taeshik Yoon doing an asymmetric 2+2 reaction. And what they find is that when they use a chiral Lewis acid, they can carry out this reaction with high levels of enantioselectivity. And the reason why this reaction works is that the Lewis acid complexes to the alpha beta unsaturated ketone and actually activates it for reduction. And so what this means is that the substrate is only reduced when the Lewis acid is complex to it, which is why they get such high levels of enantioselectivity. You can also see this type of activation in photosystem 2 of the plastiquinone cofactors. Right, so photosystem 2 needs to control electron transfer events through the system. And it turns out that it uses changes in the hydrogen bonding environment around the plastiquinone cofactor to regulate those electron transfer events. And so our thought is that we could sort of take advantage of that type of activation in sort of simpler systems. And so it turns out this actually works quite nicely. We can do a deacetoxylation of this alpha acetoxy ketone using a nicotinamide-dependent enzyme called the double bond reductase and a photocatalyst. In this case, this is rose bengal. And we can get the deacetoxylation to occur in good yields, excellent levels of enantioselectivity. We've done some calculations on this activation mode and expect the protein to activate the substrate by a couple hundred millivolts. Now, one of the things we've become interested in is whether we can apply this activation mode to EREDs. And we began to look at this in the context of changing the types of alkenes that can be reduced. So if you look at the canonical substrate binding mode, this allows us to essentially form hydrogen bonds with sp2 hybridized oxygens. And that's why this enzyme is so effective for substrates that have carbonyls or these nitro groups. What we considered is that there might actually be a possibility to take advantage of N heterocycles that would have this sp2 hybridized nitrogen that could hydrogen bond with, say, a histidine, rendering that pyridine easier to reduce. And that would allow us to think about reducing motifs that you might find in pharmaceutically important molecules. And so ultimately found out that this could be achieved. It goes without saying that no stock ER is not able to reduce these types of substrates on their own. It's only in the presence of a photoredox catalyst, in this case rubipi, that we can get the reaction to occur in good yields and good levels of enantioselectivity. And it works on a wide variety of different types of substrates. Now, when we started our study, we sort of assumed that the enzyme was activating the substrate for reduction. And what we ultimately found in this control experiment was that the enzyme wasn't essential for this reactivity. So if you replace the enzyme with just FMN and run the reaction, you can get a racemic reduction of the substrate, promising yields, obviously no enantioselectivity. And so the presence of the background reaction isn't necessarily an issue if the protein is activating the substrate for reduction, and in that competition, you only reduce substrate that's bound within the protein active site. We did a competition experiment and looked at enantioselectivity to try and gauge whether there was any enzymatic activation. And really, to our surprise, what we ended up finding is that if you look at what happens when you add excess equivalents of FMN and you look at the enantioselectivity, you can see that the enantioselectivity decreases at a rate that would be very similar to what you'd expect if there were no enzyme activation. So this was really surprising to us. We tried to understand what was going on in this case. And ultimately, what we ended up sort of stumbling on was actually looking at the nature of this radical. So we had sort of the idea that maybe this is a persistent radical. And so the way to gauge this is actually to look at the bond strength of the carbon-carbon bond that would be formed during dimerization. And while this isn't a persistent radical, which is to say that the carbon-carbon bond formed in dimerization would have a negative kcals per mole, what we end up finding is that this has a very, very weak carbon-carbon bond, about 17 kcals per mole. And so in the literature, this falls into the realm of what's referred to as dynamically stable radicals, or radicals that can dimerize but readily homolyze again. And so what we think is actually going on in this reaction is the photocatalyst reduces the substrate, forms this radical anion, which is protonated to form this benzylic radical. And then this dynamically stable radical can bind within the protein active site. And then it appears as though flavin is sort of ideally suited for quenching this radical intermediate and setting that stereo center. And so we think this is an interesting reactivity pattern that we can maybe apply to other types of reactions that actually might form carbon-carbon and carbon-nitrogen bonds in the course of the reaction. We've been able to apply this general sort of photocatalyst enzyme strategy to hydroamination reactions. What I'm showing here is just trying to evolve for higher levels of enantioselectivity for this particular radical cyclization. You can get both enantiomers, and so it's another case of being able to use a photocatalyst with an enzyme to be able to do something that the enzyme couldn't do on its own. And then what we've looked at more recently is also this idea of being able to conduct dynamic kinetic resolutions in biocatalytic reactions, right? And so normally you need substrates that can readily racemize in the presence of the enzyme, and then the enzyme will selectively react with one enantiomer. And so in general, when we're looking at these types of reactions, we're looking at sites that can readily racemize, like those adjacent to carbonyls or say these alcohols and amines that have very hydridic hydrogens. But in theory, if we were to think about using photocatalysts or maybe electrolysis synthesis to be able to form other types of radical intermediates, you could think about racemizing sites that aren't sort of readily racemizable. Of course, this might help us streamline the synthesis of various molecules. And so that's ultimately what we did. We were interested in using photoredox catalysts to be able to do a racemization. This was work that we did in collaboration with Dave McMillan. So Dave had previously reported that you could use an organocatalyst with a photocatalyst to do a beta arylation reaction. And right, mechanistically how this works is the amine will react with the ketone to form an enamine, which still has a very strong, say, allylic CH bond. But upon oxidation to the radical cation, you significantly attenuate that pKa such that it can be deprotonated to form this allylic radical, which in this case will react with a persistent radical anion to give you the beta arylated product. And so what we recognize is that we could actually use this pKa attenuation upon oxidation to facilitate a racemization. And in this case, we could actually use a thiophenol as a hydrodatum source to quench that radical to help us facilitate the racemization. And so the long and the short of it is that this actually works quite nicely. As a function of being a dynamic kinetic resolution, this has to be a one-pot, one-step reaction. And so we can use this amine catalyst, thiophenol, photoredox catalyst under aqueous conditions in the presence of an enzyme to carry out this dynamic kinetic resolution, high yields, excellent levels of diastereo and an anti-selectivity. It works on a variety of different substrates. And what I think is really attractive about this approach is that the racemization protocol operates under one set of reaction conditions, and enzymes tend to operate under very similar sets of reaction conditions. And so what this means is that we can swap the enzymes out to get to different stereoisomers. And so for instance, this is what we get with a wild type enzyme. If we move to a variant that we had evolved in-house, we can get the opposite diastereomer. We can get the opposite enantiomer using horse liver alcohol dehydrogenase. And then we have a longstanding collaboration with Prosomics. And so we tested their 384 well plate of ketoreductases to identify one that gives us the opposite enantiomer for the cis diastereomer. And so this speaks to sort of the generality of this approach. Moreover, you can think about essentially swapping this out for any enzyme that would modify a carbonyl. And so we can use transaminases in this reaction. Of course, this gives us access to chiral amines, again, high yields and anti-selectivities. And so I think there are a lot of opportunities to do various racemizations or dynamic reactions in solution, and then just use the enzyme to pull out one of the stereoisomers. And I think that this can have a really big impact on how we think about building stereochemically complex molecules that could be used for various applications. And so I think with that, I'll just conclude by saying I think there's lots of opportunities to use light with enzymes or other catalysts with enzymes to do new types of reactions that you couldn't get with either of the catalysts on their own. And so I'm really excited to see potential opportunities on that front. And so with that, I'll just conclude by thanking my group and all the folks that conducted the research. I'll thank my funding sources, and I know I'm a little bit over, but I'd be happy to take any questions you might have.
Thank you so much, Professor. So let's start with the questions from the students and postdocs. If there's no questions, can I ask maybe just like, can you both go back to the slides about charge transfer complex?
Yeah, sure.
So I'm just wondering, you said both substrates need to be bound to the complex to make the complex, or like how do you know like that both substrates must be bound to the structure?
Yeah. So what we've done, I didn't include here, is if you remove the chloroamide and you just have the styrene, you see no change in the absorption spectra. And so to us, this seems to indicate that both need to be bound within the active site for the reaction to occur. You could imagine some sort of allosteric interaction where the alkene binds on the surface. If that were the case, then I would expect that you would get more of the hydrodehalogenated product. There also aren't sort of obvious allosteric sites on the ene reductase, leading us to believe that that's likely not the case. We've done DFT calculations on these higher order complexes that we've been able to prepare using Glide or any sort of basic docking software. We've done TD-DFT on those systems as well. We're able to sort of recapitulate what we see in the UV-Vis experiments. And so I think all of that sort of evidence to us suggests that they both have to be bound within the active site. We've tried getting crystal structures. We can get crystal structures of the protein on its own, but as soon as we add the alpha chloramide or the substrate, it becomes a little bit more complicated to sort of deconvolute the electron density.
That makes sense. Thank you.
Yep.
Yep, go ahead,
Hi, Professor Hyster. Thank you very much for the very nice talk and those awesome reactions. I wonder what is the largest scale of those reactions? Are there any industry application on those reactions?
Yeah, so I mean, I think there is a lot of industrial interest in these reactions. And I think a lot of the questions surround how can you scale them? And so I would say in general, biocatalytic reactions scale reasonably well. Most pharma companies can run, reactions on, hundreds of kilo scale, and the reactions work just fine. The workups present a little bit of an issue, but I would say pharmaceutical companies have worked that out. So to me, the challenge in our case, I should add, EREDs have also been run on large scale, and so they're actually quite robust proteins to high substrate concentrations, low enzyme loadings. And so I don't see that to be the issue. I think the issue is, how do you think about running photochemical reactions on large scale? And I think that's actually a challenge that sort of permeates photoredox catalysis as well. And so I think, there's opportunities for flow, and I think there are people looking at that. We're trying to develop enzymes that operate at longer wavelengths so we can get deeper light penetration and maybe take advantage of some of the really great advances by AbbVie for doing sort of batch photochemistry. And so the largest scale we run them on are, I think, 2 gram scale. We've gone up to maybe 25 grams per liter of substrate. I think we're right around 100 weight percent enzyme, so it's still an order of magnitude higher than we'd like to be. But I think those are benchmarks that we can continue to solve using directed evolution to get to something that'll hopefully be more industrially relevant.
Cool, thank you.
Yep.
Okay, if there's no question from the students, so if there's any questions from the professors.
So I have a question. A nice talk. I got interested about you say the stereochem. Apparently, I'm not organic chemist, so it's the first time I learned about this. Seems like in the rest there's isomerization and there's a dynamic equilibrium, and then the substrate is selecting one of them and then convert it. So in addition to the chiral centers, is there any other systems that have such kind of behavior? Because I just get so inspired about the capability. There's the equilibrium, and you can only chew up one side of the equilibrium and do that. Is there any other similar concepts to that?
Yeah, let's see. I think John Hartwig has a really great example with olefin isomers, where actually EREDs will only consume one of the olefin isomers. I think that's a really great example. Yeah, I mean, one of the things that we're really interested in is if you can do sort of dynamic connectivity of a molecule where the enzyme will only, react with one of the regioisomers, what have you. As long as it's all dynamic, that could actually be a really, I think, unique way of thinking about building molecules.
And that's right, and because I tend to think about more maybe from kinetic models, because Paula says sometimes I have too many equations in mind. But my question is, what's the lifetime about isomerization in this case, and what is the time scale that the molecule should shift fast enough, and so the enzyme, this kind of effect can be observable or be utilized?
Yeah, so let's see, our racemization happens within an hour or two. Essentially, you can go from enantioenriched to racemic within an hour or two. I think one of the really nice parts about the enzyme, right, there's enough ketoreductases out there that you can find the one that's going to have the kinetic profile that you need, and then you can sort of control cofactor turnover, enzyme concentration to sort of fine tune the rates to match the rates of your racemization. And so this is something we definitely had to think about as we move to other enzymes. They would work under the reaction conditions, but the kinetic profiles would be slightly different. And so we would change the enzyme loading, tweak the amount of cofactor turnover enzyme to sort of fine tune those rates to make sure we got the highest yields. And so I think there's lots of levers for tuning those rates.
All right, great, thank you. Yeah.
Yep.
I want to ask a very simple and ignorant question, but I mean, I think the chemistry you showed is really amazing, and I really like the radical with enzymes. Yep. So I guess I was thinking while I'm sitting here, which probably will tell you how little I know about all of this. How do you even start? Like, if you want the radical chemistry, right? Do you actually look for enzymes that are known to react to radicals? Or do you, like, how do you pick? Like, if you want to work on an entirely new reaction?
Yeah, so the way that we tend to approach it, and I think maybe this is indicative of maybe my background, but we tend to look at, say, the small molecule reactions that people have done previously and try and understand the mechanisms that they've used. And then we end up looking into the enzyme literature to try and identify proteins that we think would be amenable to that type of mechanism. And so, for instance, for the dehalogenations, a lot of that was actually inspired by, I guess, Paul Melchiorri's work with charge transfer complexes, but maybe even more than that, Corey Stevenson's initial work using photoredox catalysts with Honchester as a hydrogen atom source. So I think we saw that and went, well, Honchester looks similar to NADPH, so we should use a nicotinamide-dependent enzyme to try and do that reaction. We initially had a photocatalyst present. We're getting great enantioselectivities, went back and ran the controls, found that the photocatalyst wasn't necessary, and that's what sort of set us off on that path. And then once we had that reactivity, if I'm being honest, we struggled to get other cyclization reactions to occur. And so then we started asking ourselves, what are other types of cofactors that might behave similarly to NADPH, but have different reactivity profiles? And so that turned us onto this idea of using Flavin, tested those started to do the chemistry we're interested in, and that became more general. And so, some of the questions we're asking ourselves now is, how can we do oxidative radical formation? And that has its own sort of sets of challenges associated with it. And so we're taking the same type of approach, right? What types of proteins seem to be tolerant to highly oxidizing species, and using those as starting points. And it seems to have worked reasonably well. And so I think we start on sort of the simplest possible approach to it, really based on how people think about things in small molecule catalysis. And then we go and look for the enzyme.
So what if you would want to work, or maybe you wouldn't want to work on like some reaction that doesn't have that much data in the literature?
Yeah, I would say that becomes a little bit harder. I think, right, when we're thinking about initiation mechanisms right now, we sort of keep them very simple: single electron oxidation, single electron reduction. And so at that point, I think we have enough information to know the types of cofactors that would work for that type of reaction. It becomes more complicated, right, when you start thinking about trying to do hydrogen atom transfer, things that might be a little bit more complicated. I think we might have to come up with a slightly different approach when we start moving to that.
Yeah, we can talk more about it. Yeah.
Yep.
But yeah, thank you. Nice talk.
Thank you.